Okay, so let's resume where we stopped, from where we stopped, and it was here. Okay, so we had written down the probability for producing the final state, which has the particles carrying momentum P1, P2, so and so forth up to Pn. So I am assuming I am looking at a final state which has n particles in it, and they have momenta P1, P2 and so forth. Okay, that is what you see here in this out state, and this was the expression for probability. And last time we had also looked at these last two factors which are here in this box, okay, and we wrote down its expression in terms of these matrix elements which are denoted by M here, and that those matrix elements we get by stripping off the factors that always accompany them, and also these delta functions. Okay. Now, as I have repeatedly said, that if you have delta functions in your integrals, then it's much easier to integrate things, right? Because delta functions make things very simple. So let's first see how many delta functions we have, what kind of constraints they are giving, and then we'll proceed. Okay, so that's the plan. So you have 4 delta functions here, delta 4, which says that k1 prime plus k2 prime should sum up to pi, should add up to sum over all the pi's. Okay, and another delta function saying k1 prime, k1 double prime plus k2 double prime should also equal to sum of all the external momenta. So these are 8 delta functions. Now if you go here and look at this factor, okay, you can integrate trivially over d to b perp. Okay, this integral over this exponential function gives you a delta function. So it gives you 2 pi square delta 2 k1 perp prime or k1 prime perp minus k1 double prime perp. Okay, perp is short form for perpendicular. So this will give you this delta function. Okay, so I will have then, in addition to these 8 delta functions, 2 more delta functions. So I will now write down all of these delta functions. So delta 4 k1 prime, k2 prime, okay, summation over pi, then delta 4 k1 double prime plus k2 double prime minus summation over pi, and times delta 2 k1 prime and k2 prime, the perpendicular components of them. Let's check, correct. Okay, so this is what we will work with first. Okay, now this I can write as again this delta function and in this delta function, the second one, I will replace this summation over pi by k1 prime plus k2 prime, right, because this delta function, these 4 delta functions click when summation over pi equals k1 prime plus k2 prime. Okay. So, otherwise this entire expression is 0, and because it clicks only for that value, I can replace summation over pi by k1 prime plus k2 prime. So, I will write this one as k1 double prime plus k2 double prime minus k1 prime minus k2 prime. Okay, I have just put from here times delta 2 k1 perpendicular, k1 prime perpendicular minus k1 double prime perpendicular perp. Okay. Good. So, that is what we have. Now, I will just take it to the next page. I hope I still remember how I did that. No. Okay. Command C and command V. Okay, it worked. So, this is what we are looking at. Okay. Now, let us look at this carefully. Let us look at these 6 delta functions first. Okay, we will come to these 4 delta functions at the end. So, we will look at these first, these ones. So, this is what? This is saying that the x component of k1 prime should equal to the x component of k1 double prime, and the y component of k1 prime should be equal to y component of k1 double prime. Okay. So, let me write down this thing. So, these are 6 delta functions. So, first I am writing what you get from these delta 2. So, I am just expanding delta 2. Instead of using vector notation, I will write in components. So, this is delta k1 prime x component should be equal to k1 double prime x component. Okay. See, this is a vector equation. K1 prime perpendicular minus k1 double prime perpendicular equal to 0. That is when the delta function hits. That is a vector equation. Let me write it down. Okay. These are basically 2 equations, one for x component and one for y component. That is what I am doing here. So, times delta k1 prime y minus k1 double prime y. Okay. So, delta 2 is written in this way. Now, let me write down the delta 4. I will just write down from my notebook, so that I don't have to use my brain and type it out. So, delta k1 double prime x plus k2 double prime x minus k1 prime x minus k2 prime x. Okay, that is the x component of this argument. So, that is what is here. Then I will do the same for y. Okay, this is also good. K1Z plus K2Z double prime minus K1Z prime minus K2Z prime. Okay. Then one more for the energy component. So delta of omega K1 double prime plus omega K2 double prime K1 prime. Sorry, these primes are at the wrong place. K1 prime plus omega K2 double prime minus omega K1 prime minus omega K2 prime. Okay. So I have just written them down in components. That's all I have done. So if you see here, let's look at K1 and K1 prime and K1 double prime. So this let's look at K1 prime vector and K1 double prime vector. Okay, these two. So this delta function says that the x components of these two vectors match. So x components of these two, they are equal. This delta function says that the y components of these two also are equal. How about the z components? Well, none of these says that the z components are equal. Okay, at least not directly. Now let's look at K2 prime and K2 double prime. Okay. How about them? So if you look here in this delta function, you have K1 prime x minus, there is an issue of sign. No, fine. K1 double prime x is here, K1 minus K1 prime x is here. Okay. Now this delta function, because of this delta function, this entire expression will be non-zero only when K1 double prime x is equal to K1 prime x. Okay. Otherwise this entire expression is 0. So I can put K1 double prime x is equal to K1 prime x in this entire expression. So if I do so, then K1 double prime x minus K1 prime x equal to 0 I can put here because of this delta function, and these two go away. Okay, and I am left with only K2 double prime x minus K2 prime x. Okay, so x components of K2 double prime and K2 prime, they are equal from this delta function once I use this first delta function. Okay, so x components match. How about the y components? The same thing here, K1 double prime y minus K prime y, that is equal to 0 using this delta function. Okay, and then you are left with K2 double prime y is equal to K2 prime y. So y components of K2 prime and K2 double prime, they also match. And again, I cannot say directly anything about the z components. I will have to think about it. Okay, so you cannot say about this. That's one fixing that will require one condition. Fixing something about z will require another condition, two conditions. And right now we are also left with two delta functions, this and that. Okay. So what I am going to argue next is that in fact that the z components also match. Okay. So that's what the goal is. But before I do that, let me now write this product of delta functions using the information that I have already used in making these tables. So I have delta K1 prime x. Okay. Then you have delta of K2 double prime x minus k2 prime x from this line times this line will give you delta of k2 double prime y minus k2 prime, okay, I am not being very consistent, k2 prime x, sorry, minus k2 double prime y, k2 prime y minus k2 double prime okay, sorry, I keep making mistakes. That's why I should look at my notes. k2 prime x minus k2 double prime x, k2 prime y minus k2 double prime y. Now this is better. This is correct. Okay. So this is fine. And then these remaining two. And we are going to next manipulate these two delta functions. Okay. Let's see if I can do that thing again. Okay. Okay, works. Okay, so these are the things with which we have to work now. Now, if you look at this delta function, now this delta function will click if k1 double prime z is equal to k1 prime z, and that will be nice because then it will mean that the z components also match, and also when k2 double prime z equal to k2 prime z. So all of these will, the argument of the delta function would be 0 and delta function would click. Okay. But then there is another possibility that k1 double prime z is equal to k2 prime z and k2 double prime z is equal to k1 prime z, that even then it will click. Okay. So what I will do instead is, first I will look at this delta function and then we will come to the second last delta function. Okay. So that's the idea. And let's call this equation A. There is no equation, these are, yeah, there is equality, so fine. In A. Okay. So what does it say? So we have, let me first write down. I am writing down omega k1 double prime. Okay. So let's write down omega k1 double prime. And what is that? It is k1 double prime square plus mp1 square. Okay, I will physical mass for mp, and okay, and 1 is a subscript, not for momentum, but how about this? How about we drop the p for physical mass and I will just write m1. Okay. So I am allowing for different masses for projectile and the target particles. Okay, and what is this? It is just k1 double prime x square plus k1 double prime y square, k1 double prime z square plus m1 square. Okay. Now, I have already argued that k1 double prime x is same as k1 prime x. So, I will write k1 prime x squared plus k2 prime y squared plus k1 double prime z squared plus m1 square. Okay. And this I have done using the previous delta functions, okay, because I have these delta functions which allow me to do this. Now, omega k1 double prime minus omega k1 prime is equal to 0. See, that is omega k1 double prime minus omega k1 prime. Okay, these two together could give you 0, and omega k2 double prime minus omega k2 prime could also give you 0. Okay, but and in that, if they do, then this delta function clicks. Okay, it gives you a non-zero value. But for that, just a second. For that, k1 double prime z should be equal to k1 prime z. Then only this will be satisfied, not otherwise. Okay, and also you see now that other way around, that omega k1 double prime equal to omega k2 prime. So you might think that these two together give you 0 and these two together give you 0. That's also another possibility in principle, but that's not going to work because we are allowing for different masses, so it will not work in general. Okay, so we are keeping the masses different for k1 prime and k1 prime and k2 prime, and k1 double prime and k2 double prime. So in general, that's not going to work. So we get this condition satisfied if k1 double prime z is equal to k1 prime z, and similarly omega k2 double prime minus omega k2 prime is equal to 0 if k2 double prime z is equal to k2 prime z. Okay, and which is nice. Now I can, from this one, from this one I conclude that the z components also match. Okay, now the z components match. Yeah, that's good. So the z components match, and then I can use that information in this delta function, okay, and turn it to something is not very okay. I'll think about it later if there is something sloppy in the argument, but I'll just proceed now. So what in essence you get is, looking at these two last delta functions, okay, what you get is delta k1, no, everything is fine, I guess. Okay. So, with what I have argued above, from that we get that the product of these two delta functions in the previous page should be proportional to delta of k1z double prime minus k1z prime times delta of k2z double prime minus k2z prime. Okay, that is what we expect, and then we can say that these two match. Okay. So, good, because now I can replace all these delta functions by a delta function which is saying that k1 prime is k2 prime and k1 double prime is k2 double prime. But now we should find out the Jacobian here. Okay, when you go from here to the right hand side, you will pick up some factors, and that is the factor which we need to figure out. Okay, so which one are the last delta function? What is that? Okay, we'll now look at this one, this delta function. So, the argument of the last delta function we will call it, I will see it as a function of, call it f k1 double prime z. Okay. So, let me write down, I am saying f of k1 double prime z is by definition omega k1 double prime plus omega k2 double prime minus omega k1 prime minus omega k2 prime. Okay. That is what appeared in this argument. That is what I have defined as f. Okay. Now, because we are going to manipulate these delta functions, in this delta function I will take a derivative of f with respect to k1 double prime to find out where, to find out the Jacobian. Now, this is omega k1 double prime plus this k2 prime, k2 double prime, omega k2 double prime I can write as the x component k2 prime double prime x square, but the double prime the x component of k2 double prime is same as x component of k2 prime. So, this is fine, plus again the y component of double prime is same as y component of k2 prime. So, this is okay, I can write it this way, but k2z double prime square, because this is yet to be determined. Okay. Plus mp1 square and then minus omega k1 prime minus omega k2 prime. Okay. So, let us take the derivative. And what will you get? You will get, because this involves the square roots. Okay. This is just like this one, you write a expression with square root and then differentiate, then you will get okay, that is what you get from here. Then the second term gives you 1 over 2 times this exact thing, but that thing is 2k2 double prime times the derivative of what you have in the square roots, that gives you and for that derivative I should substitute k2 double prime z to be the following. This is from the previous delta function. Okay. This expression is coming from here. Okay, so I am just substituting K2. So okay, a prime has been left. Okay, so I am just substituting K1 double prime, K2 double prime Z in terms of K1 double prime Z and these things. Okay, that's the expression here. And what do you get? You get, taking the derivative, you get 2 times K1 prime Z plus K2 prime Z minus K1 double prime Z, and then because there is a minus sign here, you get a factor of minus 1. Okay, and what is this? It is 1 over 2. Let me, if you look at this piece, this is equal to 1 over omega K2 double prime, and then K1 prime Z you can use the previous delta functions, and this will give you K2 double prime Z. Okay, and there is a minus sign here, and this one gives K1 double prime Z over omega K1 double prime. Okay, so you know that this is the modulus of this, 1 over modulus of this thing goes into the is the Jacobian. Okay, so what do we get? We get delta of K1 double prime Z plus K2 double prime Z minus K1 prime Z, minus K2 prime Z times delta of omega K1 double prime plus omega K2 double prime minus omega K1 prime K K2 prime. Okay, this product which was here, these two, is equal to 1 over modulus of this thing, this expression. Okay, times delta of K1 Z minus K1 double prime Z minus K1 prime Z times delta of K2 double prime Z minus K2 prime Z. Okay, that's what you are going to get. And this one I have written using previous delta functions. Okay, so that's the Jacobian I have obtained, and now I have earlier I had the equality of the x components of K1 and K1 prime and K1 double prime and K2 prime and K2 double prime, but now also I have equality for the z components of K1 prime and K2 double prime. Okay, so all the 6 components are matching now. Okay, so what did we get finally? We get this delta 4 times this delta 2, which came from the B perp integral K1 prime perp minus k1 double prime perp. We have shown that this is equal to double prime k2 double prime z over omega k2 double prime. Okay, that modulus times delta cube, which enforces the equality of all the three components of k1 and k2, k1 prime and k1 double prime and k2 double prime and k2 prime. Okay, this is very useful because now I can put this in the expression for the p, the momentum, the probability. Okay, so here I have now lots of delta functions and they are all nice and simple now, and I can just do this integral. Okay, so let's first count all the delta functions that we have. We have 6 here and 4 previously. See, total we had 10, right? Let's go back. Total delta functions are 10. 4 here, which says that k1 prime plus k2 prime is equal to the sum of all external momenta or the final state momenta, and then 6 of these. 6 of these we have manipulated and turned them into, apart from a Jacobian, maybe I can write here, delta 4 k1 prime plus k2 prime minus summation over pi times this Jacobian, which I have written, times this delta cube of what was that, k1 double prime minus k1 prime times delta cube of k2 double prime minus k2 prime. Okay, and this j is what? This j is 1 over this modulus thing coming from next pages. Okay, so this is what we have done now, and now I can do these integrals very easily. So I will do that thing now. So let me first write down the result and then I can explain. Integrating over k1 double prime and k2 double prime gives okay, maybe I should just tell what will happen. So I am going to integrate over k1 double prime and k2 double prime. Let's see what happens. Yeah, so I am going to integrate over this and this, and you have corresponding delta functions, right? So when you integrate over k1 double prime and use the delta function which says k1 double prime is equal to k1 prime, the three components of them, then what will happen here is this one will turn into f1 star k1 prime, and this one turn into f2 star k2 prime. Okay, and then this and this together will become f1 k1 prime mod square, right, because these will be then complex conjugates of each other, and similarly these two will give f2 tilde k2 prime mod square. Okay, that's one thing that is going to happen, and then these omega k1 double prime and omega k2 double prime, they will also turn into 2 omega k1 prime and 2 omega k2 prime, because I will be using delta functions. Okay, and what else? Okay, sorry, getting too many calls. Okay, that is one thing that will happen. And also, so there is one more place where you will have k1 double prime, which I can replace by k1 prime, and which is this Jacobian factor, right? So here also k1 double prime z will become k1 prime z, and omega k1 double prime will become omega k1, okay, because of these delta functions. So finally, you will get the following, and okay. So let me write down that thing. So P is equal to rho times L dq P1 over 2 omega P1, and this is integrated over region R1, dq Pn 2 omega Pn, it is integrated over region Rn, and I should have also included a factor of 1 over 2 pi cube that I missed. Okay, times d cube k1. Okay. Instead of k1 prime, that is what I am left with, I will write k1. Okay. K1 prime is a dummy variable, so instead of using k1 prime, I will use k1 because there is no need to carry a prime now. So I will just use k1 instead of k1 prime and k2 prime, I will use k1 and k2, they are dummy, I can do so, times f1 tilde k1 mod square. As I told you, they will convert to mod squares, mod square times 2 pi to the 4 delta 4 k1 plus k2 minus summation over pi, that is this delta function which we never touched, okay, and times the Jacobian factor, which is 1 over k1 prime z over omega k1 no primes now, k1 z over omega k1 minus k2 z over omega k2 modulus of that. Looks like I have taken care of all the, no, I have missed factors of 1 over 2 omega k1 to omega k2. Okay, this is the result that I have now. Okay, my bad, I should not have dropped the primes, I should still keep the primes. That's otherwise I will be inconsistent with my notation. I will tell you why I have put it back. This is k1 prime, and these that is also prime. Okay, let's keep these primes careful. Okay, the reason I should not use k1 and k2 because in the beginning I said that the momenta of these incoming particles are localized at k1 and k2 somewhere here. Yeah, see, this k1 is not dummy because I told you that the momentum of here these wave packets are such that they are concentrated around K2, okay, meaning they have a, the peak is around K2. So K2 is not a dummy variable. I should not have said that I can replace by K2. And similarly K1, the wave packet, the wave function of this particle, okay, that peaks around K1 in the momentum space. So here, that's why I have kept these things. Okay. Now what I will do is, I will use the fact that f1 tilde and f2 tilde, they are sharply peaked around K1. So you can think of them as Gaussian functions peaking at K1. K1 prime is equal to K1 and K2 prime is equal to K2. Okay. And we have already talked about the normalization of these functions. So what was the normalization? Here, the normalization was this. If you take f2 tilde and mod square it and integrate over the momentum divided by this 2 omega, then that gives you 1. Okay. So in the limit that it is sharply peaked, I can, where is it? Yeah. In the limit it is sharply peaked, I can replace K1 prime by K1 and K2 prime by K2, because you can think of these as delta functions. Okay, so they hit only when K1 prime is equal to K1 and K2 prime equal to K2. So in that case, wherever K1 prime and K2 prime appear in this expression, I will replace by K1 and K2, okay, because it picks only those values from, because of the delta function or a very sharply peaked Gaussian. And then I use the normalization that you just saw and replace this integral d cube K1 prime over 2 omega K1 prime f tilde 1 K1 prime mod square by 1, and similarly this one, these two together by 1, okay, and then you get the following final result. P is equal to rho times L times okay, times 2 pi to the 4 delta 4 K1, just a second, what happened? Yeah, K1 plus K2 minus summation over Pi. Okay, that is this delta function where K1 and K2 have been, K1 prime and K2 prime have been replaced by K1 and K2 times 1 over 2 omega K1, 1 over 2 omega K2, 1 over K1z over omega K1 minus K2z over omega K2 modulus of that times m of K1 K2 giving P1 to Pn, and we have to do a mod square of it, okay, because of Here I had missed writing down mod square. I will not write the arguments now. This factor should have been there. So this is what you get finally. Okay, it has become very nice and simple. Okay, I'll do a little more of massaging of this thing later, but for now let's see what we have got. So apart from these factors, which are basically 1 divided by energy of the incoming particle k1 and 1 over the energy of the second particle, k2, and then you have mod m square. That is what you have to calculate. Okay, so the entire information about the dynamics of what process is happening, okay, and what kind of interactions are there is contained in this amplitude, this matrix element m, okay, and the mod square of it. So this is the piece which really knows about the dynamics or the interactions. Okay. The remaining factors are kinematic factors. Okay, and you are integrating over all the final state in here. And this rho L and L, they do not have anything to do with the nature of interaction or the dynamics. It is just that there are too many particles and these densities and all these things are involved. So the real content is contained in the factor which is multiplying rho times L. So all these things. Okay, and this is what we will look at carefully. Actually, I can give you an exercise. Yeah, it will be better. So exercise number 1, look at this line and argue that this is a object which is invariant under boosts along the z direction. Okay, so it's not invariant under complete Lorentz transformations, but only if you restrict transformations along the z direction, then this line is invariant, and all other quantities are invariant in this expression. So P is invariant under boosts along the z axis, and z axis is the beam axis. Okay, so I will define d and sigma, it is a definition, d cube p1 to d cube pn is equal to, so I am writing down these factors now. So this is basically integral. Okay, let me first write down, then it will be easy to understand. 1 over 2 pi cube 1 over 2 omega p1 times 1 over 2 pi cube 2 omega pn. So these are these things, these factors here, times 2 pi 4 delta 4 k1 plus k2 minus summation over pi. This is this factor times mod m square okay, and there is one more factor which is going to come from this line, and you can show that this is 1 over 4 k1 dot k2 whole square, where n1 and m2 are the masses of particle with momentum k1 and particle with momentum k2. Okay, so that's the expression. this expression, which is really what you have here, if you were to take these differentials on the right and integrate over them and multiply with rho and L, you will get P. Okay. So, stripping out rho and L, whatever is left behind, okay, the differential of it is called the differential cross section. Okay. So, this is a fully differential cross section. Okay, we will do more with these differential cross sections later in the course, but now we have made a full connection with the experiment. Okay, I can go and calculate these differential cross sections, or I can do some integrals over these cross sections, differential cross sections, and get some integrated over cross sections, and that I can calculate because I can calculate mod m squares, and mod m squares I can calculate because they are related to the Green's functions. Remember, these are mod m squares or m, the matrix element is basically S matrix element from which you have removed some delta functions and some other factors of 2 pi's. And we have already seen that S matrix elements are related by LSZ reduction, we had related them to amputated Green's functions. So, now you can write down Green's functions using Feynman diagrams and calculate m. Once you have m for a particular process, you multiply with these things and integrate over some momenta if you wish, and that gives you, after multiplication with rho and L, gives you probability of producing that particular final state. Okay. So, you have a calculation from theory side now, which you can match with the experiments. Okay. So, we have now completed our connection, making the connection with the experiments, and we have an expression in general for a fully differential cross section. Okay. And you see, in these steps, I never made use of the fact that I am looking only at scalar interactions. Okay. You have this result is general. The differences that will come from having different kinds of particles will all be contained in the calculation of mod m square. Okay. But this formula is general otherwise. Okay. So, I will say a little more maybe next time. Yeah. So, we will stop here.